A supernova is a great combustion caused by a star that is dying. A supernova happens approximately once every 100 years. The explosion forces matter into space and can shine as bright as an entire galaxy for a short amount of time. Supernovas can even briefly outshine entire galaxies and radiate more energy than our sun will ever in its entire lifetime.
There are two situations in which a supernova can form. The first is a type 1a supernova, and the second is a type 2 supernova. Before a type 1 supernova begins its course, two stars exist by orbiting each other. The stars generate heat through the nuclear reaction from hydrogen fusion creating helium. At a certain point in the star's life, each star will expand into hydrogen. After becoming a red giant, the star's core will contract, producing heat to fuse helium into carbon and other elements. The radiation generated from the fusion will push away the outer layers of the red giant, and the core will remain. The core is called a white dwarf. Usually, one will become a white dwarf while the other is still a red giant. The white dwarf's gravitational pull will suck the red giant's outer layer into its atmosphere. After reaching 1.4 solar masses, a nuclear chain reaction will cause the white dwarf to explode and the red giant to move away due to the loss of the computational orbit of the white dwarf. Stars of many large sizes can experience a type 2 supernova. Two counteracting forces stabilize a star. Gravity pulls the star's matter inward, while the star's inward pressure of heated gas pushes the matter out. Like stars that undergo type 1 supernovas, heat is helium. When the stars run out of hydrogen, it contracts to generate heat and fuse helium to form carbon and oxygen. The star will contract again to fuse carbon and oxygen to form neon and magnesium. The contraction is repeated to form silicon and sulfur. An infusion of atoms creates layers of heat energy to counterbalance gravity's inward pull. A fourth contraction forms iron. However, when iron fuses, it does not release an energy source to counteract the star's gravity, and the star collapses into itself. The collapse releases additional energy in a shock wave that begins a cataclysmic explosion. What remains is a spinning core of neutrons, called a neutron star. More massive stars will leave behind a black hole.
A supernova burns for a short period of time, but it can tell scientists a lot about the universe. One kind of supernova has shown scientists that we live in an expanding universe, one that is growing at an ever-increasing rate. Scientists have also determined that supernovas play a key role in distributing elements throughout the universe. When stars explode, it shoots elements and debris into space. Many of the elements we find here on Earth are made of the core of stars. These elements try to form from new stars, planets, and everything else in the universe. Cosmologists rely on the light produced by supernovae to map out the contour of distant galaxies. According to cosmological maps, they relied on how bright astronomers assume supernovas are. But these calculations are fraught by some uncertainty, since determining the true brightness of an object millions of light years away is a tricky business. The ideal solution to this problem would be to find a type of supernova so close that astronomers could analyze the star before and after the detonation to determine the exact brightness.